Hi dear friends, this is Sonni, Assistant Professor, Department of Chemistry, Arts, Commerce and Science College, Jawar, District Palghar. Dear friends, in the previous part of the video, we have discussed about the stereoisomerism or the stereoisomers and the various types of stereoisomers. Particularly in the previous lecture, we have studied about the stereoisomers called as geometrical isomers and optical isomers. We have also discussed about the condition for the geometrical isomers and the optical isomers, and definitely we have discussed their types in detail with the various examples. Dear friends, in the same video we have discussed about the stereochemistry of carbon compound containing a one asymmetric carbon atom, and during that discussion, we came to know the term about enantiomers and the racemic mixture. Dear friends, today in this part of the video, we are going to study about the stereochemistry of carbon compound with two dissymmetric or asymmetric carbon atom. Here in this discussion, we will talk about the compound containing more than one, means the two asymmetric carbon atom. If we'll discuss here, the set of four groups attached to the asymmetric carbon atom are different, at least in one group, then they are called as a dissimilar asymmetric carbon atom. And the number of stereoisomeric forms in this case is given by the formula 2 raised to n that we discussed in the previous part. And as in this lecture, we are going to talk about the molecule containing the two asymmetric carbon atom, means here the value of n, number of asymmetric carbon atom, will be 2, and that's why in this case the number of stereoisomers possible is 2 raised to n, means that is equal to 4. So here in this molecule, that is nothing but the 2 bromo 3 hydroxy butane molecule. In this case, definitely we will talk about the different stereoisomers which are possible, and these 4 possible isomers are given by the structure number 1, 2, 3 and the 4, and definitely we will see the relationship between these two also. If we talk about the structure number 1 and structure number 2, structure number 1 and structure number 3, okay, these are not mirror images of each other, and you know the stereoisomers which are not mirror images of each other are called as diastereomers. Similarly, the structure number 1 and the structure number 4 is also not mirror images of each other. That's why the structure number 1 and 4 is also the diastereomers of each other. Again, if we talk about the structure number 2 and the structure number 3, definitely these are also not mirror images of each other. Similarly, structure number 2 and the structure number 4 are also not mirror images of each other, and hence the structure number 1 and 3, 1 and 4, 2 and 3 and 2 and 4, 2 and 3 and 2 and 4 are not mirror images of each other, and hence these are called as the diastereomers of each other. Here we will discuss. So here this is the something problem here, I must say. Hence this structure number 1 and 3, 1 and 4, 2 and 3, 2 and 4 are not mirror images of each other, and such stereoisomers of a molecule which are not mirror images of each other are called as diastereomers. So it is also known as diastereoisomers, and that's why the diastereoisomers can be defined as the stereoisomers which are not mirror images of each other are called as diastereomers, and diastereomers must contain more than one asymmetric center or the chiral center. There are some characteristics which are shown by means of a diastereomer, is that the pair of diastereomers has similar configuration at least one asymmetric carbon atom. They differ in optical rotation and amount of rotation in direction or both. They are differ in their physical properties like melting point, boiling point, density, solubility, etc. And they are also differ in their chemical reactivity and rate of reaction with the other optically active compound. And important, this shows or they exhibit different physiological activity. So this is the very important thing regarding with the diastereomers. So if we will try to distinguish between enantiomer and diastereomers, then here it is very simple. Enantiomers are the optical isomers which are non-superimposable mirror images of each other, while diastereomers, these are the optical isomers which are also non-superimposable, but they are not mirror images of each other. Again, molecule even with one chiral carbon atom can have enantiomer, but in the diastereomer it has at least two asymmetric carbon atom to show the diastereomers. They rotate the plane of plane polarized light by the same amount but in opposite direction, where diastereomers may rotate the plane of plane polarized light by different amount in different direction. They have same physical properties like melting point, boiling point, etc. But diastereomers are having different physical properties. They have some same chemical reactivity and different rate of reaction with the other optically active compound. But here diastereomers have slight differ in chemical reactivity and rate of reaction with the other optically active compound. Enantiomers cannot be separated by fractional distillation or fractional crystallization, but diastereomers can be separated by a repeated fractional distillation or fractional crystallization. So dear friends, in this way, we will talk about the stereochemistry of carbon compound with similar asymmetric carbon, because if you'll see in the earlier example, then you will come to that both the asymmetric carbon was different, it was having the different groups attached to the particular asymmetric carbon. But here you see, here this is COH, at this carbon there is also COH, here OH, here it is also OH. So both the asymmetric carbons are having the identical groups, different identical groups, and this molecule is called as a tartaric acid. This molecule is called as tartaric acid. So it has two asymmetric carbon atoms which are similar, and therefore the expected number of stereoisomers will be again same 4, and these 4 stereoisomers possible are 1, 2, 3 and 4. Definitely if you will see the structure number 1 and the structure number 2, then the structure number 1 and structure number 2, these are non-superimposable mirror images of each other, hence these two are called as enantiomer. So one of them is D form, dextrorotatory form, and the other is levorotatory. But the structure number 1 and 3 as well as structure number 2 and 3 are not mirror images of each other, hence these are diastereomers. But if we talk about the relationship between structure number these two, that is 3 and 4, then structure number 3 is optically inactive, because this structure number 3 is having the plane of symmetry. You can see here this molecule is having the plane of symmetry, that's why the structure number 3 is optically inactive form. Now if we'll see the relationship between these two, then the rotation of one asymmetric carbon is cancelled by the optical rotation of other carbon in the structure number 3. Okay, regarding the structure number 4, actually structure number 4 is looks like the mirror image of structure number 3, you can see here. But if we'll see, the rotation of structure number 4 gives a structure number 3 exactly, it gives the structure of, see you can see here, actually this is the mirror images, these are the mirror images of each other, but if this mirror image is rotated by means of an 180 degree, then this is exactly superimposable on the structure number 3. It means that structure number 4 is the superimposable mirror image of structure number 3. It means that the structure number 3 and the structure number 4 are not different, these are identical. So in practice, total number of stereoisomers from the compound containing similar asymmetric carbon is only 3 and not 1, because the two structures are having the plane of symmetry. So these are called as meso compound, which are optically inactive. And the characteristic of meso compound can be defined here. The meso compound is optically inactive due to internal compensation. These always contain a plane of symmetry. Again, physical properties of mesoform is different than the enantiomer, and all achiral means optically inactive compounds are called as mesoforms. Optically inactive forms are called as mesoforms in this type. Now the next part, which is very important, this is called as a configuration. Whenever you want to define the configuration, definitely configuration is very important to know the arrangement of groups or group of atom or the atom present in the molecule, and from the configuration we are able to define the exact three-dimensional structure of the molecule, and that's why we should be able to define the configuration. Actually, the configuration is divided into two types. The first one is called as the relative configuration, and the second one is called as the absolute configuration. First of all, we will talk about the relative configuration. When the configuration of molecule is compared with the configuration of some other standard or reference molecule, then it is called as relative configuration. Here, in order to determine the relative configuration of the given molecule, the standard reference molecule is chosen, and that standard reference molecule is called as the glyceraldehyde. Glyceraldehyde is having the structure like this, that is CHO, CHOH, CH2H, and this relative configuration is again divided into two types based upon the position of OH group attached to asymmetric carbon, because this glyceraldehyde is having only one asymmetric carbon atom, which is indicated by star this here, and this relative configuration is divided into two types based upon the position of this OH group attached to this asymmetric carbon atom. And the first type of the relative configuration is called as the D configuration. When the OH group attached to the asymmetric carbon atom is present on the right hand side, then it is called as the D configuration, and the structure will look like here. So you can see here, this OH group attached to the asymmetric carbon is present on the right hand side. That's what is called as the D configuration. The next one is the L configuration. So similarly in this structure, when the OH group present or OH group attached to the symmetric carbon atom is present on the left hand side, then it is known as L configuration. So you can see here, this is the structure in which OH group attached to the symmetric carbon atom is present on the left hand side. So this is the L configuration, and that's what the name of the structure or the name of this molecule will be L-glyceraldehyde. T and L system of nomenclature does not explain the configuration of each chiral atom, each chiral center or asymmetric center, and when a molecule contains more than two or more than one asymmetric center, definitely this system is not convenient, and therefore for the molecule containing more than two chiral center or the asymmetric carbon, the another notations are used which are known as erythros and the threos. Definitely this term is used because relative configuration capital D and capital D, E and capital L does not explain the configuration of each and every asymmetric carbon atom, and that's why if the molecule containing more than one asymmetric carbon atom or the chiral center, then the another notations are used called as erythros and the threos. What is erythros isomer? Here, when the two similar groups in a projection formulae are present on the same side, it's very important, then the isomer is called as erythros. Here you can say, so this is and this is, both are the symmetric carbon atom, but here similar groups are attached to the symmetric carbon atoms are present on the same side. That's why it is called as erythros, and this is the structure of sugar actually, and that's why it is called as D-erythros. Actually here this is the tartaric acid, but here in this tartaric acid it has the two asymmetric carbon atom, and both the symmetric carbon atoms have the similar groups on the same side. That's why the name of this molecule is called as erythrotartaric acid. And if the two identical groups attached to the asymmetric carbon atom are present on the opposite side, then it will be called as the threos here. And for the tartaric acid, as this OH and this OH, or H and OH, these are on the opposite side. This OH and this OH are on the opposite side attached to both the symmetric carbon atom. That's why it is called as a threo, and it is the structure of tartaric acid. That's why this molecule is called as a threotartaric acid. So dear friends, in this way we try to define the stereochemistry of the carbon compound containing two asymmetric carbon atom, either different asymmetric carbon atom or same asymmetric carbon atom. But definitely if the molecule is containing more, that is two similar asymmetric carbon atom, then the expected number of stereoisomers is not 4 and it is 3 because of the two structures are containing or having the plane of symmetry. This is the important thing regarding with the major compound and which are optically inactive. So dear friends, in this way we studied about the stereochemistry of carbon compound containing two asymmetric carbon atom as well as relative configuration. And in the next part of the video we will talk about the configuration, particularly absolute configuration, which is very important to describe the three-dimensional structure of the given molecule as well as conformational isomerism of the alkane, means the compound containing carbon-carbon single bond. So thank you. We will resume in the next part of the video. Thank you very much.